Hi, welcome to the ComSci 137 lecture. Sunny here. This module, we will discuss bandwidth utilization. Let's start. Bandwidth utilization is the wise use of available bandwidth to achieve specific goals. Efficiency can be achieved by multiplexing. Privacy and anti-jamming can be achieved by spread spectrum. Multiplexing is the set of techniques that allow the simultaneous transmission of multiple signals across a single data link. As data and telecommunication use increases, so does traffic. We can accommodate this increase by continuing to add individual links each time a new channel is needed, or we can install higher bandwidth links and use each to carry multiple signals. Today's technology includes high bandwidth media such as optical fiber and terrestrial and satellite microwaves. Each has a bandwidth far in excess of that needed for the average transmission signal. If the bandwidth of a link is greater than the bandwidth needs of the devices connected to it, the bandwidth is wasted. An efficient system maximizes the utilization of all resources. Bandwidth is one of the most precious resources we have in data communications. In the figure, the word link refers to the physical path. The word channel refers to the portion of a link that carries a transmission between a given pair of lines. One link can have many channels. There are three basic multiplexing techniques: frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. The first two are techniques designed for analog signals, the third for digital signals. Frequency division multiplexing is an analog technique that can be applied when the bandwidth of a link is greater than the combined bandwidths of the signals to be transmitted. In FDM, signals generated by each sending device modulate different carrier frequencies. These modulated signals are then combined into a single composite signal that can be transported by the link. Carrier frequencies are separated by sufficient bandwidth to accommodate the modulated signal. These bandwidth ranges are the channels to which the various signals travel. Channels can be separated by strips of unused bandwidth called guard bands to prevent signals from overlapping. In addition, carrier frequencies must not interfere with the original data frequencies. To maximize the efficiency of their infrastructure, telephone companies have traditionally multiplexed signals from lower bandwidth lines onto higher bandwidth lines. In this way, many switch or leased lines can be combined into fewer but bigger channels. For analog lines, FDM is used. One of these hierarchical systems used by telephone companies is made up of groups, supergroups, master groups, and jumbo groups. 12 voice channels are multiplexed onto a higher bandwidth line to create a group. A group has 48 kHz of bandwidth and support 12 voice channels. At the next level, up to 5 groups can be multiplexed to create a composite signal called a supergroup. A supergroup has a 240 kHz and support up to 60 voice channels. So on. Other applications of FDM are AM and FM radio broadcasting, television broadcasting, and first generation of cellular phones.
Wavelength division multiplexing is designed to use the high data rate capability of fiber optic cable. The optical fiber data rate is higher than the data rate of metallic transmission cable, but using a fiber optic cable for a single line wastes the available bandwidth. Multiplexing allows us to combine several lines into one. WDM is conceptually the same as FDM, except that the multiplexing and demultiplexing involve optical signals transmitted through fiber optic channels. One application is the SONET network. A newer method called dense WDM can multiplex a very large number of channels by spacing channels very close to one another. Time division multiplexing is a digital multiplexing technique for combining several low-rate digital channels into one high-rate channel. Instead of sharing a portion of the bandwidth, the time is shared. There are two different schemes, synchronous TDM and statistical TDM. In synchronous TDM, each input connection has an allotment in the output even if it is not sending data. The data flow of each input connection is divided into units, where each input occupies one input time slot. A unit can be one bit, one character, or one block of data. In synchronous TDM, the data rate of the leak is n times faster, and the unit duration is n times shorter. What if the data rates of the inputs are different? We use multi-level multiplexing, where the data rate of the input is a multiple of other inputs. In multiple slot allocation, more than one slot per input. In pulse stuffing, we add dummy bits to inputs with lower rates. Framing bits follow a pattern, frame to frame, that allows the demultiplexer to synchronize with the incoming stream so that it can separate the time slots accurately. Here, in multi-level multiplexing, we add the two inputs. In multiple slot allocation, we divided the input. In pulse stuffing, we add the dummy bits. Here is the framing bits. In statistical TDM, slots are dynamically allocated to improve bandwidth efficiency. Only when an input line has a slot's worth of data to send, it is given a slot in the output frame. In statistical multiplexing, the number of slots in each frame is less than the number of input lines. The multiplexer checks each input line in round-robin fashion. It allocates a slot for an input line if the line has data to send. Otherwise, it skips the line and checks the next line. Address field is needed in each frame. The data size to address size ratio must be reasonable. There are no synchronization bits, and the capacity of the link is normally less than the sum of the capacities of each channel. You can see here the difference between synchronous and statistical TDM. In synchronous TDM, some slots are empty because the corresponding lines does not have data to send. In statistical TDM, there is no slot left empty as long as there are data to be sent by any input line. Also, the output slot in synchronous TDM is totally occupied by data. In statistical TDM, a slot needs to carry data as well as the address of the destination. In synchronous TDM, you can see the framing bits. Spread spectrum is designed to be used in wireless applications. In wireless applications, all stations use air as a medium for communication. Stations must be able to share this medium without interception by an eavesdropper and without being subject to jamming from a malicious intruder. The main technique is to add redundancy. If the required bandwidth is B, the bandwidth for spread spectrum is greater than B. Signals are spread with different codes so that they can be separated at the receivers. The spreading process must occur after the signal is created by the source. One technique is the frequency hopping spread spectrum. It uses M-carrier frequencies modulated by the source signal. Modulation happens one carrier frequency after another. A pseudo-random noise creates a k-bit pattern for every hopping period t sub h. The frequency table uses a pattern to find the frequency to be used for a hopping period and pass it to the frequency synthesizer. The frequency synthesizer creates the carrier signal of the selected frequency. Here is the k-bit pattern generated by the pseudo-random noise. As you can see, the first pattern is 101, which corresponds to 700 kHz in the frequency table. The source signal modulates this frequency. The next pattern is 111, which corresponds to 900 kHz, so the source signal modulates this frequency. The next pattern, 001, it corresponds to 300 kHz, so it modulates this frequency, and so on. Here is an example of 4 channels using FDM and 4 channels using FHSS. In FDM, each station uses one-fourth of the bandwidth, but the allocation is fixed. In FHSS, each station uses one-fourth of the bandwidth, but the allocation changes hop to hop. Another spreading technique is the direct sequence spread spectrum. The technique replaces each data bit with n bits using a spreading code called chips. The chip rate is n times that of the data bit. As an example, let us consider the sequence used in wireless LAN, the famous Barker sequence where n is 11. When the original sign bit is 1, the produced spread signal follows the spreading code. If the value is 0, the produced spread signal is the inverse of the spreading code. This ends Module 9. Thank you.